back to the slide. Okay, I hope I no, this is hold on. So okay, this is another consideration, an issue that impacts some application of the fraction non-conforming control chart. It's over dispersion, the sample size ranges dramatically from the very small number to the very significantly large size. When sample sizes are very large, this over dispersion, which is going to cause more variability in the data than is predicted by the binomial distribution in essence. And which also results in control limits that are too narrow. And this leads to identification of too many false alarms. The data will indicating the out of control conditions or the signals. So over dispersion is caused by by many things that are inherently transitory, so such as weather prediction, fluctuation, different operators, unusual variation in a small batch of material, and so on and so forth. So they are not really assignable costs that can be fairly easily identified, and they are part of the process that are very difficult, if not possible, to identify assignable causes, and then that can be removed accordingly. So this approach that can be suggested to dealing with this is to use the individuals in control chart, also apply to the fraction non-conforming data. That is helpful, however, it is not necessary to tell us the problem has can be solved by 100%. So Lanny, 2002, has suggested a modification of traditional P-chart that deals with over dispersion and combines the within sample variability measured by standard deviation of the individual PI sample value. That says reflecting the sigma z, and with the estimate of the between sample variability. So this estimate is obtained by first converting the individual PI value into standardized ZI, yeah, and value using the equation 7.14 in the textbook, and using the span to moving range to compute the estimate of standard deviation of the ZI value. The ZI value sigma z called the sigma z. Then the z, so z will be a new variable we calculate the standard deviation of the z. Then the control limit for the Lanny P or P branch can be constructed as follows. So if no standard is available for P, then the average from the sample P bar can be utilized. Note that if the standard deviation of the z, that the standardized score is close to unity, there will be little difference between the standard PE chart and the Lanny chart. Then to illustrate, consider the data in table 7.7, which represent the non-conformance data for 20 consecutive weeks of hospital emergency department data records. So in this case, the sample size are relatively large and that can lead to overdispersion, which reflect to the standard deviation, standard p-value in the figure. Yeah, it's quite small. So like this is overdispersion. Okay. Then by using the Minitab individual moving range chart for the fraction non-conforming, so it can be modified and rectified accordingly. So the LANIP can also be used when the data have under dispersion as well. So finally, for the figure 7.13 and finally the figure 7.14 show the LANIP and the p-prime chart from using the Minitab for the fraction non-conforming data. Now no point out of control, the average error rate is still too high, about 9.5%. Like this. Yeah, it's just quite high. Then, so corrective action to improve the process are necessary. So sigma z 3.87 is a considerably larger than the unity. So there's a quite strong evidence of the overdispersion in this data set. Okay, then we move to the 7.3. Control chart for the non-conformity, the defect, number of defect. A non-conforming unit does not satisfy one or more of the specification known as a spec. Each point where a specification is not satisfied is considered a defect or non-conformity. So non-conforming unit contain at least one non-conformity. However, the unit with defects are not necessary to be non-conforming items or non-conforming products. So it is often useful to work directly with a number of the defects. So it is possible to develop control chart for either the total number of non-conformities in a unit, single unit, we sum it up over the entire unit, or the average number of non-conformity per unit. So this control chart usually assumes that the occurrence of non-conformities in samples of constant size is well modeled by Poisson distribution. Then essentially, this requires that the number of opportunities or potential locations for non-conformities can be infinitely large. Yeah, that the probability of occurrence of the non-conformity in any location is so small. So this average, so the average probability should remain constant. Furthermore, the inspection unit must be the same for each sample. And that is to say, each inspection unit must always represent an identical area of opportunity for the occurrence of non-conformities. So then in most practical situations, this condition will not be satisfied 100% exactly or more specifically. The number of opportunities for the occurrence of the non-conformity may be finite, or the probability of occurrence of the non-conformities may not be constant. So as long as this departure from the assumption we had before, we had in this constant, or the deviation from the assumption is not severe, the Poisson model will usually work reasonably well. There are cases, however, in which Poisson model is completely inappropriate. So this situation will be discussed later in the chapter 3. So now move to the section 3.1, procedure with constant sample size. So this is the most cases that will be that is encountered realistically. So consider the occurrence of non-conformity in the inspection unit of product. So in most cases, the inspection unit will be a single unit of the product, only one single product. Although this is not necessarily always to be so. So the inspection unit is simply an entity for which it is convenient to keep records on that. It will be a group of 5 units of product. The inspection unit of product, or 10 units of product, or 15. Suppose that the defects or non-conformities occur in this inspection unit according to the Poisson distribution, like we have addressed this in the sophomore year elementary statistics courses, where X is a number of the non-conformity and C is a constant parameter is of the Poisson distribution. So that will be the parameter related to the frequency that occur according to that non-conformity. I'm sorry. So that will be the C, and then therefore a control chart for defects or non-conformities, or the C control chart with 3 sigma limits can be defined as follows, like a C plus or minus 3 standard deviation, like this. Then control chart for non-conformities, no standard given. Then center line, you'll be replaced the average of the total number of the non-conformity within a single unit. The control limit in equation 7.7 should be regarded as a trial control limits. The preliminary sample example lack of control in the usual phase 1 analysis. So the control chart for non-conformity is also sometimes called the C chart. So this is example. Then table 7.7 represent the number of non-conformity observed in 26 successive samples of the 100 PCB board. So it is noteworthy that for reasons of convenience, the inspection unit is defined as 100 boards. Yeah. Set up C chart for those data. So just sum them up over the 100 PC board independently. So since the 26 sample contain 516 total non-conformities, we estimate C by 516 over 26 sample, 26 units. And the C bar is 19.85. Therefore, the trial control limit are given by that. Take the square root of the C bar, upper bound going to be 33.22, center line is located at the 19.85, the lower going to be 6.48. So based upon the illustration in figure 7.12. Investigation, there's a 2-point. Extrapolate the control limit. Outside the control limit, sample 6 and 20. Investigation of sample 6 revealed that a new inspector has examined the board in this sample and that it did not recognize several of the types of nonconformity due to the lack of experience, domain experience that could have been present. Furthermore, the unusually large number of nonconformity in sample number 20, as can be seen from here, result from temperature control problem in the wave soldering machine, which was subsequently repaired then. Therefore, it seems reasonable to exclude these 2 samples and revise the trial control limits, since we found assignable causes correspondingly. The estimate of C is now computed as center 19.67, upper lower the 3397, lower 6.36. Finally, then that becomes standard value against which production in the next period can be compared and monitored. So 20 new sample each consists of the 1 inspection unit that is made that's made of the 100 board are subsequently collected and monitored. The number of nonconformity in each sample is noted and recorded in the table 7.8, like here, and the 27 until the 46. Then no lack of control is indicated. However, the number of nonconforming per board is still high, quite unacceptably high. Well, you can see that is quite high. Yeah, even though it's within. However, this is not quite high. So further action is necessary to improve the entire process. So further analysis of nonconformities. Defect or nonconformity data are always more informative than fraction nonconforming. The C chart, the defect or nonconformity is much more informative than only the percentage, because there will usually be several different types of nonconformities. By analyze the nonconformity by type, we can often gain the insightful or considerable insight into their potential causes. This can be of considerable assistance in developing the OCAPs. OCAPs stands for out of control action plans that must be accompany control chart. Once I would like to further analyze what is subsequent action, subsequent instruction that should guide the practitioner proceed in order to perform for the quality improvement. So, for example, in the printed circuit board process, and there are 16 different types of the defects. Defect data for 500 board are plotted in the Parabto chart in figure 7.14, like here. So this is a Parabto chart, okay? Done. So, however, note that over 60% of the total number of defects is due to 2 defect type, solder insufficiency and the solder cold joints. Insufficiency and the cold joints. So this point to further problems with the wave soldering process. So if this problem can be isolated and separate and then eliminate, there will be a dramatic increase in process yield. That's for sure. So in such a circumstances, the process adjustment or the process qualification or even process improvement by using the design of experiment can be warranted. So notice that the non-conformities follow the Pareto distribution. That is to say, most of the defects are attributable to only a few, in this case, to defect type. That would be more appropriate to accommodate all of the defect types. So this process manufactures several different types of the PCB boards. Therefore, it might be helpful to examine the occurrence of the defect type by type of the PCB board. So table 7.10 presents this information. Cause and effect diagram. Yes. So not all the 40 solder insufficiency on all the solder co-joint occur in the same part number. So this implies that this particular type of the board is very susceptible to problem in wave soldering, and the special attention must directed or paid toward improving the state of the process for this part number. Okay, particular the part number on the same part number 0.001 to 85. This table 7.10 table. Let me check. I'm sorry. Table. No, this is in the textbook. I'm sorry. Then also cause and effect diagram will be really helping, and the defect and printing circuit inspection that is related to the measurement, the test coverage, inspect soldering process, spreader, change speed and weight pumping, flux and temperature, roll car, the short circuit shroud, and the moisture content missing from rail, and the component insertion, the chrome operator, and the automation. So choice of the sample size, the U chart. So example 3.7.3 illustrates a control chart for non-conformity with the sample size exactly equal to 1 inspection unit. That inspection unit chosen for operational or data collection simplicity. In order to exercise this practice easily, then, however, there's no reason why the sample size must be restricted to 1 inspection unit sometime. In fact, we would rather prefer to use the several inspection units in some cases, and thereby increase the area of opportunity for the occurrence of non-conformities. The sample size should be chosen according to the statistical consideration or practical circumstances such as specifying a sample size large enough to ensure a positive lower control limit. So sometimes it is a lower 0. There's no sense. So it shows a larger the sample size to decrease the standard deviation or standard error to get at least a positive lower bound, lower limit. So to obtain particular probability of detecting a process shift, since we like to increase sample size for safeguarding the power for detectability. Alternatively, economic factor could also taken into consideration into the sample size determination. So suppose that we decide to build the control chart on a sample size of n inspection unit, and does not have to be an integer. To illustrate example 7.3, we will specify a subgrouping like an n 2.5 inspection unit and so on and so forth. So total size, the sample size become 2.5 times 100. So yeah, this is not just 250 board. So there are two general approaches to constructing the revised control chart once a new sample size has been selected. So on the other hand, one approach is simply to redefine a new inspection unit that is equal to n times the old inspection unit. In such a case, the center line on the new control chart will be defined as n C bar, and the control limit are located n C bar plus or minus 3 square root of n C bar. And C bar is observed mean number of the non-conformity in the original inspection unit. Suppose that is so that's multiplied by n is a sample size. How going to change the size of the unit? So in example 7.3, after revising the trial control limits, we decide to use a sample size of n equal 2.5 inspection units. Then center line we have been relocated from 19.67 to 49.18, and control limit have been revised to 28.14 and 70.22, like here. So second approach involves setting up a control chart based upon the average number of the non-conformity per inspection unit. If we find the X total non-conformity in a single sample of the n inspection unit divided by n, then the average number of non-conformity per inspection unit can be found through the equation 7.18. So know that X is a Poisson random variable. Consequently, the parameters of the control chart for the average number of non-conformities per unit can be given in the equation 7.19. The mu bar plus or minus 3 standard deviation mu bar divided by n. So yes, this individual mu bar, this divide, this is n squared. So mu bar represents the observed average number of non-conformities per unit in a preliminary set of data. And the control limit found from equation 7.19 will be regarded as a trial control limit. So this per unit chart, often called the control chart for non-conformities, or typically called U chart here. I would like to draw your attention. So this mu is equal the mu bar. So like we mentioned, you call the x over n, x over n. X over n. So since for each one is independent, so this is minus the mu bar divided by n. So it's a standard deviation. So this is the, since we Poisson have the same variance, divided by n. Divide by n, and this variance divided by n, sigma squared divided by n, take the square root, going to be the standard deviation. Okay, this is example. A supply chain engineering group monitors shipments of raw materials to the company distribution center or distribution network. Errors on either the delivered material or the accompanying documentation are tracked on a weekly basis. So each week, 50 randomly selected shipments are examined and examined, and the errors are recorded. The data for 20 weeks are shown in table 7.11. Set up a U control chart to monitor the process. As according to the equation, the mu bar can be computed as a 0.0740, and the parameter of the control chart plus the take the square root 0.70740 divided by 50, the sample size. Then the upper control limit, lower control limit per unit is about 1894. The lower bound parameter of the control limit, so it's not possible to be negative. So minus 0.0414 should be reset to 0. So since lower control limit is less than 0, set up to default as 0 for U chart, the control chart shown in the figure 7.19. The preliminary data do not exhibit lack of statistical control. Therefore, the trial control limits given here will be adopted for phase 2 analysis, monitor of the future observation, the future operation. Once again, note that although the process encounter every number of error per shipment, still really high. Actions should be taken into consideration in order to improve the supply chain system. Okay, I stop here. I think it is really late in Sydney now. It is already almost 1:35, so I need to stop here. Okay, thanks for your listening. I will back in the next Wednesday. See you then.